Hello and welcome to They're Just Robots, podcast on robotic control, brought to you by Enforced Social Isolation and Harun Sheikh.
Thought you had plenty of friends, more than you could ever really want. But really, sometimes they're not what you need. They can't do it all, cause they're only human. True kind of pal would drop all that she's doing. You need a true friend, and we've got lots. They're just ROBOTS robots.
And we're back with the episode 10 of They're Just Robots. Last time we discussed the supervised learning challenges and perspectives in robotics as seen 30 years ago. And as you may remember, there was a mention of reinforced learning, as in there is this thing called reinforced learning, but we're not really sure how would it fly in robotics. So today we're giving a perspective on exactly how well did reinforced learning affect robotics, machine learning in general, and how did it look like in 2013. So yeah, exactly 25 years after the paper we analyzed in episode 9, there was a paper that was covering the reinforced learning in robotics as a survey. And this paper by Jens Kolber and his collaborators is again a joy to read, as surveys often are, because they distill the knowledge, they have the opportunity to give nice parallels, nice examples, and to make some sort of a grand vision for a whole field. Or in this case, two fields, robotics and reinforced learning. And the authors really start with a nice example. They compare reinforced learning and robotics, their relationship, with the relationship of maths and physics. And as you may guess, in this parallel, it is the reinforced learning that's the maths, and robotics is the physics. In the sense that the learning part, the people who do reinforced learning have this amazing creativity and can study different problems that have limited touch with the practical reality, or just study a different reality, because not all of the problems in learning or science altogether are related to mechanics, as in robots. So it's the robotics with its particularities, with its physicality, that reminds the mathematicians, okay, this is what we need. We can't really ignore gravity. We don't have a 10-dimensional space here. We're acting in 3D. But actually, as you will see, it's worse. It's not 3D. It's usually like 20D. So let's start with the problem of reinforced learning straight away. We start from a state. Think of robots' current position, current velocity, current acceleration, current orientation, that sort of thing. A state. And we perform an action. This action gets us into another state. This action is performed according to a certain behavior. We'll call that behavior a policy. And for moving from state 1 to state 2, we're going to be rewarded. And consecutively moving from state to state to state to state will give us a cumulative award. So all the rewards are going to add up. And simply put, it is our goal to find the policy, so to find the rules of behavior that will give us the biggest reward. So the biggest cumulative reward is our goal, and whatever gives us that, that's the behavior we want. And that's what reinforced learning is all about. Under Markovian assumptions, it doesn't really matter what brought us to a particular state. It's that state and that state only that defines what's going to happen when we move to the next state. So we can relatively safely ignore history under the terms of a Markovian system. If the system is not Markovian, well, things can fail, but we hope they won't. So, reinforced learning. There are two ways to do it, really. One is to learn the value of every state in the world. I mean, not that state and not that world. Every state in the state space. If you know those, then you just jump around with the biggest value, with the biggest reward, and you get your optimal behavior, you get your optimal policy. The other option is you have a policy and you try improving it some more, tuning it, fine-tuning it, and you get to a perfect example of the policy you started off with. I mean, practice makes perfect. So it's those two families of reinforced learning solutions that we're going to cover in this podcast. Doing the value function-based methods or doing policy-based methods.
That dog is man's best friend. That might very well be true. But every bone that a canine buries, but to do better, steadfast and truer. Fetch any stick, bring your papers, slippers, available in fur, and they don't need wax, they're just ROBOTS
If this podcast ever grows to something more, I'll have an episode. I'll have a whole season on optimal control. But right now we have to pretend it doesn't exist because you may have not heard of it yet. So optimal control, this thing that doesn't exist, is very similar to reinforced learning. It also aims to find the optimal policy, the optimal hopping between states to get to the destination, to get the highest reward. It's just that in optimal control, you have the model, you have the system. So pretty much you know exactly what happens when you move from a certain state to the next state. It's deterministically defined. In learning, as we have seen, it's pretty much the lack of the model that guides us, that pretty much pushed us into the whole learning thing altogether. So we can't really rely on something like optimal control. But this is where you start connecting the dots, and you may ask, so how about adaptive optimal control then? So start from a very crude model and learn to tune its parameters. So you'll be fine with only knowing the structure, only knowing the qualitative behavior, maybe. And then you just quantifiably tune it. I mean, sure, in all fairness, that could work. And some scholars would say that that's pretty much what reinforced learning is all about. So let me warn you right away. Reinforced learning and robotics, they may have not gotten along well in the early beginning, because robotics has this issue of partially observed states. There are so many states, as I told you. If you have a lot of degrees of freedom, and all of a sudden from 7 degrees of freedom, and in a space in which you are supposed to perform something, you end up with a 20-dimensional space that is continuous in its physicality. So you have an exponential explosion of states, and you need to keep track of all of them to give an optimal solution. And at the same time, the whole world is so noisy. There's so much uncertainty introduced by both your manipulator, your environment, your measurements. So you can already see what some of the issues may have been. And also, the whole learning story is the story of repeat, try again, repeat more, try more. Maybe this works, maybe that works. And in robotics, that's pretty expensive. You usually have a limited time to use the robot. There's a limited physical ability of the said robot. There is probably limited finances. So you will have to heavily extrapolate from whatever you get from your real robot. And if possible, rely to models. Models, that's a whole different can of worms, which has the issue of propagating errors so fast that the whatever you learn on a model might end up looking very weird and very bad on the robot itself. And of course, there's the issue of what exactly a reward should be, because it probably is not defined perfectly and exactly by the physicality of the task. It will probably involve some black magic to shape the reward. And it takes a roboticist to do it, because what machine learning people find interesting and the theorems they have and the maths they want to do, that's probably not that relevant to the issues a roboticist may have where they want to apply machine learning. Speaking of rewards, do you want to sum up all the rewards from today to the end of the world and keep track of that and say that's the function you're trying to optimize? Or maybe you want to keep the average reward at a certain level, and that's something you're trying to optimize to get the maximum average reward. Or maybe you are living in the moment and you want the rewards to come now, and the rewards that come later, you just multiply them by a small coefficient and say they don't matter that much. These infinite horizons are difficult to grasp and to solve optimally for in robotics cases. And at the same time, the whole diminishing terms in the future can cause instability in robotic scenarios as well. So averaging is cool if your horizon is finite. So if you pretty much know that your episode is going to end at some point, there is an end to your task, that it's not just going to continue on and on. And another thing I wanted to mention in these preliminaries is the exploration versus exploitation trade-off. You may have heard it already. There is a soft spot somewhere between being exploratory, trying all the options, and exploitation, using the best option you found so far and going for a reward, instead of just going around and thinking about the ways to solve problems. And that soft spot keeps on moving and keeps on changing. I mean, with problems like, say, this current pandemic, you have to start exploitation fast. You have to do it right away. Even if you're wrong, that's fine to an extent, because you just couldn't have afforded to sit on your hands and keep thinking, keep exploring the landscape. You have to act. But in a different scenario, if you don't explore, you get eaten by a lion, which probably could have been avoided if you had just looked around, did some scouting, and you probably weren't in that much of a rush. So exploration versus exploitation trade-off is a particular issue for a particular problem. Now, You remember that I told you optimal control doesn't exist in the universe of this podcast. Optimization also kinda doesn't exist because we didn't cover it in this course. You probably didn't cover it to this extent in previous courses. So there is this thing called optimization problems, gradient descent, Karush-Kuhn-Tucker conditions, they all don't exist. And in this non-existent realm, there is something called the primal problem and the dual problem. They're essentially the same optimization problem, but expressed in different ways, and usually mean that you're optimizing via different functions. And here it turns out, if you express your optimization problem, your reinforcement learning in one way, you're doing policy search. Remember, you have a policy, you're polishing it, no pun intended, and you're trying to get the best out of it. You just move around and fix it slightly every time you do something. In the dual interpretation of the problem, you're doing value function based search. So you're going around through the states of the world, again, states of the state space, and trying to assess their value. Their value in the sense of how much reward you're going to get after doing everything right from that state onwards. So you leave that state and you play the best you can. So how good can you get? If it's good, sure, that state might be something relevant to your task, to your learning objective. If it's bad, maybe you shouldn't have gotten to that space altogether, to that part of state space altogether. Maybe just go somewhere else. While at it, you can also have a relationship between the state and the action. So for this state and for this action, how good is it? So this transition, how well can I profit from it? That's where you get something called state action value function, which is Q. And you may have heard of Q learning. We're going to go back to Q learning at some point during the next episode. So if you're doing your value function optimization, you're doing two different steps. One is policy evaluation, which is your system entering particular states, measuring the value, doing that until the value converges to a stable state, to a stable value, and then you just improve your policy based on a very simple, very myopic, greedy algorithm. So just hop from the state in which you are to the next state with the greatest reward, with the greatest value. And sure enough, that works great if you actually have the access to the model, if you can keep on doing your policy evaluation all the time on something relevant. If you can't, then you probably have to do something like Monte Carlo evaluation of the policy in the real life. So you will, for a short time, evaluate the policy, try to estimate states in the real system, on the real, do the rollout, and then you randomize when you go back. And you keep churning, you keep trying to evaluate the big picture. Or again, if you have the access to something relevant at every time step, you can do something called temporal difference algorithm, where you update your state not based on the big picture, but just what was your estimate in the previous step, what's your estimate now. There's an error in between. Based on that error, you just update your state value for the state you are in.
Cut your hair and look after your mother. Make your soup when you're sick of all the things that
All that we have mentioned is, as we've seen, tricky for robotics because we don't really expect to be able to do our full search of the state space, update all the values, and have the values really crisp. We already said there's so much noise, so much uncertainty. And if you don't have the exact values of the value function, you may encounter problems because the optimal strategy, the optimal policy can only be determined if you have the optimal values. If you don't, it's going to deviate and it's not probably not going to converge to whatever you wanted. So if you want to play it safe in robotics using your favorite reinforced learning methods, go for policy search. It's what you would call domain appropriate, as you can include some expert knowledge in the structure and also include some expert knowledge in the initialization of the policy. So you can start from a policy that you have an idea about, that might work, that you know already. Now, why reinforced learning people love the previous approach with the value functions is because it can be optimally solved. Again, the things that don't exist. Optimization, optimal control, all that works much better with the value functions. With the policy, you can't really directly solve it, but it scales better, which is great because we need that scaling. You remember we have exponential combinatorial explosion of space in robotics, so everything that scales well is good for us. Now again, the bad word, optimization. You're optimizing policy locally. So the policy is going to change by a delta every now and then to fit, to improve. But that pretty much means that the policy can't all of a sudden become something extremely different. You can't invent an essentially different behavior. You're going to stay in the neighborhood of whatever the initial behavior was. And as such, you will get into an optimum. It just might be a local one. Because you're probably doing something like a gradient method. You're climbing a hill. You approximate your gradient. You find where the largest gradient is, so where the hill is steepest, and you're going there because it optimizes your reward. And here we have to think about the reward as something physical as well. It's just easier. So you might make your reward consume as little energy as you can to get in this particular state and perform a particular task while avoiding something else. So the avoidance means that you're not getting penalized. The low energy consumption means that you're not getting penalized by the energy part, and getting there means you get the reward of the goal. So while trying to achieve all that, you need to estimate just how the function there looks like and how the gradient of it looks like. That's again something that's a task of optimization theory, and there are some pretty decent methods. So policy-based optimization is cool. The optimal value function based optimization is even cooler, but not really applicable in that form to robotics, which pretty much means that we could use some hybrids. Sometimes we call the value function approach critic only because it examines the whole state space, it examines all the values, and then from them it just extracts the strategy by using a greedy algorithm. While we call the policy-based approaches actor-only approaches, as they keep on acting, keep on doing things, and keep on acting on the policy. So value-based one made an effect on the policy at its very end. So when it finished its critic stage, while the actor-only approaches don't have a critic stage. They just keep on doing. They learn by doing. And we can combine these and get a family of methods that's called actor-critic methods. So you use the best of both worlds. And that's again something we're going to see more of in this course.
Technology is our Lord, given to us by a friend. Pathways of current and sound, hoping to find a bite that's not sure but
Real world is hard. This message was brought to you by the roboticists, not the reinforced learning people. I mean, look at it once again. The curse of dimensionality that you have in robotics if you try to learn things about it. You have all these points in a huge world. If you try to discretize them, if you take 1 millimeter as your reference length, all of a sudden it changes with powers of 10 to the power of minus 3 times 10 to the power of minus 3, that's 10 to the power of minus 6, times once again, that's 10 to the power of minus 9, versus the ability to do things in meters. So the scale is just immense and very much depends on a particular problem you're solving. So now you have to have tricks. You have to have ways to reduce the dimensionality of your space to be able to learn anything meaningfully. One option is to make some sort of a grid world. So you can start calling places in that big state space of, as we said, it could be 20 dimensions. You can start calling parts of it bottom left, top right, and it might be enough. Because imagine playing tennis with a really big racket and being able to hit the ball back as long as you're in the right part of the court. So you just have to be left or right or forward or backward, and that's it. Just be there. The magical racket will do the thing. So you have already reduced your state space from the resolution of every little tiny square inch of your court to 4 big squares. Now that's just you being an expert, but you could also extract that division of space from the data. Maybe you just observe the games of multiple tennis players and see that the ability to return the ball just depends on where they stand. And you all of a sudden get this generated new grid reduced in dimensionality. Or you just discover that the whole state, all the states and maybe the values of them are actually described by functions. That's not too surprising because things tend to be continuous. Things tend to be described by functions, by Gaussians, by something relatively linear. Now, a lot of linear functions combined with a lot of uncertainty might turn out to be highly nonlinear and something that's very hard to approximate, and approximations of which can be catastrophic. So tread carefully, but it could be fine. Also, in all the attempts to reduce dimensionality, you may just want to reduce the actions you can make into some sort of sub-actions. This is where the whole story of hierarchical control naturally comes in again. So instead of having this painfully well-defined set of motions that move your arm from this angle to that angle, you may just have a task that's called a forehand, a backhand, and be able to deliver that particular motion in this particular part of space and just solve your problem straight away without defining exactly what the pitch angle and everything else needs to be. Now, as I already said, this works in an approximation of a really big racket, really low net, and your opponent being really lousy probably. But yes, real world is hard. It has all this noise. It's so costly to turn on and off your robot again because your robot is probably somewhere in an assembly line or in a nuclear reactor, or it's somewhere where you just can't afford to come in and out. Can I test it again? No, you can't. We don't let people do that here. And of course, even if you have the access, there is the issues of real time. So all of this, say, updating strategies, learning, optimizing, it all has to happen in between two time steps of actually executing the robotic motion. You have the issue of your world being continuous while your learning system is discrete. You have the issue of delays because you will have your samples from the sensors and samplers going to the actuators being out of sync. So all of that can immensely affect whatever your learning algorithm is, no matter how ideally it works in this ideal mathematical world of reinforced learning. And don't even get me started on the models. You can have this almost perfect model that has just a tiny difference in a certain parameter. But as the motion starts evolving on such a model, and as you learn something on such a model, you actually focus, your algorithm tends to focus on that tiny difference and exploits it. That's what we call undermodeling. And it's just like overfitting for supervised learning. When you just fit to all the peculiarities of your training data and you miss the big picture completely while trying to follow religiously the training data. Here you follow religiously the quirks of your and all of a sudden when you deploy the whole thing on the real system, you discover it doesn't work. It starts from a similar position, but it turns out to be completely different. You can have a similar situation in a related condition where you learn from observing someone. If I'm a sailor and I learn how to tie knots from an old captain who knows it all and does it very fast, I see it, but as soon as I lose track, as soon as I make one mistake in doing it myself, someone who actually knows things would just backtrack and be able to fix it on the fly. But I would just proceed doing whatever I saw there from my experienced teacher and fail to get the final result because I made a mistake in the somewhere in the middle that just propagated. Now, the lucky thing is if your system has some sort of damping, some sort of self-stabilizing mechanism that just draws it back to whatever the state is, has a lot of inertia, you might actually transfer the knowledge from the model because these small errors would be diminished by the sheer inertia of the model itself, by its self-stabilizing properties. If not, it just gets worse by the second. You know why else the world is difficult? Rackets are really small. So if I'm playing tennis now, and if I make my reward system to be simply this: if you get the ball over the net, that's good, you get a cookie. If not, you have failed. The odds are I'm never going to learn how to play tennis because it's very hard for me to hit the ball on random, especially if I don't know that I have to go towards the ball. I don't know under which angle I should hit it to try and getting it over the net, because I might hit it and get it over in the stands or somewhere. So you have to modify your reward for me. You have to do some sort of pedagogical reward shaping and tell me, okay, that was close. So maybe I was close to hitting the ball. Or even better, I hit the ball and I was close to getting it over the net. It just hit the net or hit the ground before the net. So even if it's a binary task, you either did it or not, you need to have a gradual progression of rewards. You need to shape the rewards in a non-binary fashion. Sometimes you can extract these rewards from an expert demonstration. You actually learn to reward your motion if it's close to whatever was achieved by the expert. But that, again, is tricky because you're restricted to just whatever you saw there. You will never discover that things can be done in a different way. Unlike the real world that is hard, robotics is easy because we can always just refer to previous episodes of this podcast and solve really tough problems. So remember when we did trajectory planning, when we just approximated everything with splines and via points and just said, okay, the only important parts of my trajectory are these via points and the initial and boundary conditions. Everything else settles by itself because it's a polynomial. Well, you can actually do the same for policy, and you usually do, because it would be painstakingly hard to define a policy for every millimeter movement you make. So you just approximate the policy with splines. You approximate it with your parabolic blends, whatever you want. And again, referring back to when we did hierarchical control, you can do hierarchies in learning as well. So if you need to perform a complex movement of a relatively complex manipulator, let's say you're moving a leg, you may want to break it down into tasks that are performed by the independent parts and then just assemble it together into the movement of the whole leg. So you can have the knee, the ankle, the thigh moving separately, and you can learn those motions separately and then combine them into something meaningful. Or you can take a different approach and do everything together, but start from a simpler task that can be by something very similar to transfer learning, moved into more complex motions. So literally, you can learn how to crawl, then you can learn how to walk, and then you can learn how to walk. I mean run, of course. As most surveys, this one also ends with questions to be answered by the future. And again, with the hindsight of 7 years since this survey appeared, we maybe have some answers. We'll have to wait for the next episode. But the question was, for instance, what to approximate. So you have to approximate something in robotics. Does it have to be the policy? Does it have to be the value function? Does it have to be the space? All of it? Just parts of it? What can we keep intact? How can we generate reward functions from data? What's the best way to incorporate the prior knowledge? Is there a way to use active perception, or we just have to take this dumb measurements of the environment? What about the robustness in parameters? because if we make our models very robust to protect them from the effects of error spreading when deployed, they actually stop being real models and they start being something very uncertain and something that doubts in itself all the time. So why bother? If you make everything Bayesian, you're just too conservative. So with that in mind, we have something to discuss in the next episode as well. Where are we 7 years after this survey? So if the robot had a task to break a mirror 7 years ago, the curse is probably lifted, and maybe, just maybe, our reinforced learning is even better now. And what the whole fuss is about deep learning. Stay tuned for the next episode of They're Just Robots.
Don't be afraid, 'cause they're made of metal. They still got plenty of heart. You should think of it like it was a garden. There's fruit on the trees and you can pick it. Just don't piss them off, 'cause robots don't stick it. You need some friends and we've got them lost. They're just our robots.